In this video, we're going to learn what an integral is and how to do them. So to learn about this, let's go ahead and set up a problem. An object moving in a straight line has a velocity v in meters per second that varies with time t in seconds according to the function v equals 4 plus 1/2 t squared. Let's first start by making a graph of this function. So to do that, we're going to first of all get some data. So we'll make a data table where we are going to collect time and we're going to collect velocities for each time. And we'll get the velocity at those times, 0 through 7 seconds. So there's our data table, and now we're going to go ahead and graph that. So here's our coordinate system where time is on the horizontal axis, velocity is on the vertical axis. The horizontal axis is going to have increments of 1 second, so 1, 2, 3, all the way up to 7. Our vertical axis is going to have increments of 2.5 going up to 30. So now we just need to plot our data and see what we get. So that's roughly what our graph looks like. So we want to do a couple of things now that we have the graph and we see what it looks like. First of all, we want to do a little bit of review here, and let's figure out what the acceleration is going to be at 2 seconds. So the first question here is, what is the acceleration at t equals 2? Okay, so one way that you could do this is we know from a velocity graph to get acceleration, that's going to be the slope at that point. So there's our tangent line to it. We can find that slope. Okay, but we know a more sophisticated way of doing this, and that's using calculus. And so remember that derivative is the calculus version of a slope. So acceleration is the derivative of velocity. So that's going to be the derivative of the function 4 plus 1/2 t squared. So 4 plus 1/2 t squared. Okay, so you do the derivative of each term, derivative of a constant. So in other words, the slope of a constant is 0. So that first term goes away. And then we have 1/2 t squared. Remember, you bring the 2 down, times 1/2 times t to the 1. You subtract 1 from the exponent, and so that leaves us with just t. And then we can plug in t equals 2 to that, and we just get 2 meters per second squared. What we want to do is figure out, for part B, we want to figure out what the displacement is, delta x, for the first 6 seconds. Okay, so how could we figure out displacement from our velocity graph? So remember, displacement from a velocity time graph is equal to area under the curve. And how can we figure out the area under this curve? Well, one way you could do this is you could, so for that first 6 seconds, one way to do this is you could approximate it by maybe setting up a triangle like this. Okay, but hopefully you can see, if I do that, what the problem is. And the problem is we have this little bit of area that's going outside of the curve, and we don't want that. Okay, so we could approximate it by finding the area of that triangle, but it's probably not going to be very good. Okay, another thing you could do is you could, so a lot of times when we had shapes that were not a triangle or a rectangle, we split it up into triangles and rectangles. So what we could try to do is split this curve up, so we want all the way to 6 seconds. What we could do is split the curve up into a bunch of rectangles, okay, where the height of the rectangle, let's say this rectangle right here, the height of this rectangle is going to be the function, right? So, or the velocity rather. So the height is going to be v, and then the length is going to be some length in time. So v times delta t, right? So velocity at this time times this length of time here. And we could just keep splitting it up equal intervals of time, where the height of it is going to be whatever the function gives us at that time, and the width of it is going to be the time interval that we're talking about. Okay, so we could split this up. So we could split this up a bunch of times like this into small rectangles, and you can still see that there's going to be an issue. We're going to underestimate this, right? So we have these little chunks of area that we're not going to be counting if we do that. So how could we fix that then? Well, what we could do is increase the number of rectangles, right? So what we could do is decrease this time interval, delta t, to smaller time intervals. But then the problem is you're going to have to calculate this a lot of times, right? So this is how you could estimate the area under the curve. If we want a perfect value for the area under the curve, that's where calculus comes in, and that's where we use integrals. So here's what we know so far, okay? If you have a position time graph and you want to get to velocity time, you take derivative. Okay, and same thing, if you have velocity time and you want to get to acceleration versus time, you're taking derivative. Okay, if you want to go the other way, so from acceleration to velocity, you're taking integrals. Okay, we used to take area under the curve, and that's basically what an integral is. It's a fancy way to take the area. It's a fancy way to sum things up. So you're doing an integral to get from velocity to position or displacement. So how do we take an integral? Well, first of all, an integral is sometimes called an antiderivative. And we basically just reverse the process of finding the derivative, at least for polynomials. If you look at your equation sheet under the calculus column, you'll see, remember, we have our derivative functions where so far we've learned how to take derivatives of polynomials. And if you go a little bit below that, you'll see the integrals. And here we're going to look at how to take an integral of a polynomial. So we'll copy this one over here. Okay, so to do an integral of the function x to the n, this is the notation here, you add 1 to your exponent, so it's n plus 1, x to the n plus 1, and then you divide by that new exponent. Okay, it's just the reverse of what we were doing before. Instead of dropping the exponent and then subtracting 1 from the exponent, now you are adding 1 to the exponent and then dividing the function by that new exponent. Okay, this doesn't work for n. This doesn't work if n is equal to -1. If n is equal to -1 and you try this, you're going to get 1 over -1 plus 1, which can't happen. You can't do 1 divided by 0. Okay, and we'll learn how to deal with this if n is -1. All right, so let's try this on the function that we have so that we can get displacement. Okay, and we're going to follow this notation here. So displacement, delta x, equals, we have integral of our function for velocity, v dt. Okay, and I should note here, to go along with the notation here, on the top and bottom of your integral, you are putting your initial value and your final value. Okay, so those are called limits of your integral. And here our limits are going to be in terms of time, and we're starting at time equals 0, and we are ending at time equals 6 seconds. Okay, if we want the displacement after 6 seconds. If the question were, so this is kind of going back to where we set up our rectangles here, and we had these time intervals. Okay, so we're going from the starting point all the way to the final point. If I ask for the displacement for times 3 through 5 seconds, let's just say, then you would do integral of 3 to 5 seconds when you do this. All right, so let's look at how to take this integral. All right, so let's plug in our function. We have integral from 0 to 6 of, our function is 4 plus 1/2 t squared. And just like before, we can tackle these terms one at a time. And if we do that, if we take the integral of the first term, the integral of the first term is just going to be 4t, okay? Technically, you could say 4 is equal to 4 times t to the 0, because t to the 0 is just 1. And when you do the integral of 4t to the 0, that's going to give you, if we follow this notation, you add 1 to the exponent, so that's 4t to the 1, and then you divide by that new exponent, so divide by 1, and that gives you 4t. Okay, and just a little check here, if you take the derivative of this, that should give you what we started with, and the derivative of 4t is just 4, so that works. All right, so we have 4t, and now we need to do the integral of this second term, and so we have 1/2 t, we add 1 to the exponent, so it's going to be 2 plus 1 is 3, and now we divide by the new exponent, so divide by 3, and that's going to give us a 1/6 t cubed. Okay, again, you can take the derivative of this just to be sure. So the derivative of this is going to be 3/6 t squared, which is 1/2 t squared. So that's the right integral. Okay, so now we're left with 4t plus 1/6 t cubed. After you take the integral, you have to evaluate it with the limits that we have. So we're evaluating from our starting point, which is 0 seconds, up to our final point, which is 6 seconds. The way you evaluate this is you plug in the top limit into your function, and then you subtract and you plug in the bottom limit into your function. So it's going to look like this. Delta x equals, we'll plug in the 6, so that's 4 times 6, plus 1/6 times 6 cubed, and then we're going to subtract, and now we're going to plug in the bottom limit to our function. So it's going to be 0 plus 0, which is just 0, so that doesn't even matter. And we end up with a displacement of 24 plus 36, which gives us a displacement of 60 meter. So now that you have seen integrals for the first time, let's try to use integrals and calculus in general and see if we can't derive the kinematic equations that we've been using. So I'll put those up on the screen so you know what I'm talking about, and we're going to look at how we actually get those. Here are these 3 kinematic equations, and at first I said these are the equations that we use for motion, and I didn't tell you how we get there. Okay, but now we can actually look at how those are derived. So first of all, these only work if acceleration is constant. So acceleration is a constant. Okay, so we need to start with that assumption. And what we also know is that acceleration is the derivative of velocity with respect to time, and velocity is the integral of acceleration with respect to time. All right, so we need to start there. Okay, so if you forget how to set up integrals, but you're comfortable with derivatives, I just want to show you what you can do here. And this will help us get started with deriving these. If I solve for dv here, which I can do by just multiplying both sides by dt, then we get dv is equal to acceleration times dt. If I want to know the change in velocity over some interval of time, then we can do an integral on both sides. And we're going to go from velocity initial v naught to some velocity v, any velocity that we want. So I'm just going to label that v. And this is what we're going to solve for here in just a second. The initial velocity v naught is going to happen at time equals, we'll start our time at 0. The velocity that we're trying to get happens at some later time t. The lower limits of each integral have to correspond, and the upper limits of each integral have to correspond. The integral of just dv is v, and we're going to evaluate that from v naught up to v, which is just going to give us v minus v naught. So really quick, why is it that the integral of, let's say, dx is just equal to x? Technically, you could think of there being a 1 right here. The integral of a constant is going to give you that constant times the variable. You could think of it like this. Technically, this is 1 times x to the 0. And then using the integrals that we've been looking at, the equation, we add 1 to our exponent, so 1 x to the 1, and then we divide by the new exponent over 1. So we just end up with x. So that's why integral of dv just gives us v. So this is the left side of our equation. So we have v minus v naught equals integral from 0 to t of a dt. So now we can do that integral, and we just end up with a times t evaluated from 0 to t. Now you plug in the top limit, and then we subtract, and then plug in the bottom limit. So this will be a times t minus a times 0. So we just get a times t. And so now we're left with v minus v naught is equal to a times t. And then solving for v, we get v naught plus a t, which is one of the kinematic equations that we have. Now we want to solve for another kinematic equation, and the way we can start that is by setting this velocity equal to, this is the derivative of x with respect to time. And we're going to set that equal to v naught plus at. Okay, so we'll multiply both sides by a dt again. So we'll have dx is equal to v naught plus at all times dt. Okay, and now we're going to integrate both sides, and our bottom limit is going to be our starting position on the left side, and our upper limit is going to be some position x that we want to solve for. Okay, again, the limits have to correspond, so we'll start at t equals 0, and we'll end at some time t. The left side, same thing, we're just going to end up with x minus x naught. On the right side, we're going to do the integral of v naught, which is a constant. It could be 0 or it could be any number. Okay, the integral of a constant is just that constant times the variable, so v naught times t, plus, so technically there's a 1 up here, right? It's a times t to the 1. So if we do that integral, it's going to be a times t, we add 1 to the exponent, so that's t squared, and then we divide by that new exponent. So divide by 2. And I can solve for x now and get x is equal to x naught plus v naught t plus, and I can rewrite this as 1/2 a t squared. So here's another kinematic equation. The last kinematic equation is tricky to get. So acceleration, let's start here. Acceleration equals derivative of velocity with respect to time. To get the last kinematic equation, the trick is to multiply this side by dx over dx. Then we can rearrange it as dv over dx times dx over dt. Then dx over dt, that's just velocity. So now we can write everything as a equals dv over dx times velocity. Now we can multiply both sides by dx. And so now on the left side, we have a dx, and on the right side, we're going to have v dv. So now we integrate both sides, and we're going to go from x, the initial x value, which we may not want it to be 0, right? So we're going to say x is equal to x naught, and we're going to go to some final x value that we'll just call x. Velocity, we're going to start at some initial velocity, v naught, and end at some final velocity. And again, the upper limits have to correspond, so we end up at some final velocity at the final position, and we're starting at some final velocity, or we're starting at some initial velocity based on some initial position x. So now we just need to integrate both sides. So starting with the left side, a is a constant, and so the integral of a dx is just going to be equal to a times x, evaluated from the initial to the final position, which is just equal to a times x minus x naught, if we plug each of those in. And we'll leave it like that for now. Okay, the other side, we have integral v naught to v of v dv. The integral of v, so is going to be v, we add 1 to the exponent, so it'll be a 2 instead of a 1, and then we divide by that new exponent. So that's going to be equal to 1/2 times, and now we plug in each limit, so v squared minus v naught squared. And now we can set those two sides equal. And so we have a 1/2 v squared minus v naught squared is equal to a times x minus x naught. Now we multiply both sides by 2, and we get v squared minus v naught squared equals 2a x minus x naught. And then solving for velocity, we get v squared equals initial velocity squared plus 2a x minus x naught. And this is the last equation on the list right here. So that one's a bit tricky to get to.